Hello viewers, today we are going to discuss Poisson distribution. Poisson distribution was discovered by the French mathematician and physicist Simon Denis Poisson in 1837. Poisson distribution is also a discrete distribution. He derived it as a limiting case of binomial distribution. For, for binomial distribution, for n trials the binomial distribution is q plus p की power n. q plus p की power n. The probability of x successes is given by probability of x is equal to x, that is equal to f x n and p. N and p are parameter, that is equal to how we can define binomial distribution and cx p की power x q की power n minus x, where x is equal to 0 1 2 to so on n. So Poisson distribution is the limiting case of binomial distribution under the following condition. So what are those conditions? First is n, the number of trial is very large. That is, you can say n goes to infinity. Second, p, the probability of success for each trial, the probability of success for each trial is very small, that is p goes to 0. And third is n into p, that is equal to some constant that will be lambda. So, lambda, and this is finite. N into p is finite, that is if we take np equal to lambda, then it must be finite. So thus we can find p is equal to lambda by n and q is equal to 1 minus p, so 1 minus lambda by n, where lambda is a positive real number, so lambda is greater than 0, and this belongs to R. Lambda is a positive real number, right? So now we define Poisson distribution. Let x be a random variable, or we can say a random variable x is said to be a random variable capital X is said to be have a Poisson distribution with parameter lambda. If its probability function is given by probability function is given by probability of x is equal to x, that is equal to f of x with parameter lambda, or sometime be denoted by fx, and that is equal to e to the power minus lambda, lambda to the power x by x factorial, for x is equal to 0, 1, 2, to so on, and 0 otherwise. Where lambda is known as the parameter of Poisson distribution. Since the number of trials is very large, right? N is very large, and probability of success P is very small. So it is clear that the event is rare event. So therefore, Poisson distribution relates to rare events, right? So it relates to rare events because the N is very large, number of trials is very large, and the probability of success it is very small. So sometimes we call this event, we call this Poisson distribution, this related to the rare event. For example, uh, number of blinds born in a town in a particular year. In a particular year. So it is a rare event. So for rare event, we use Poisson distribution. The number of printing mistakes per page of the book, of the reputed book. So it is the number of mistakes in a reputed books, it is very less. So when the event is rare, then we use Poisson distribution. Even number of air accident in some unit of time, number of suicides reported in a particular city, number of defecting material in a packing manufactured by a good concern, number of telephone calls received at a particular telephone exchange in some unit of times, right? Number of faulty blades in a packet of 100 blades. So these are some rare events. Number of students scoring very high marks in all subjects. So these are the rare events. So now the next content is how we can find if the distribution function, probability function is given, how we can find the mean and variance. So the next topic is mean and variance. Let this be example. The mean and variance of Poisson distribution are given as expectation of x, that is equal to lambda, and variance of x is equal to lambda. So mean and variance of a Poisson distribution are same and that are equal to lambda respectively. So how we can find that mean is lambda, mean of a Poisson distribution is lambda, and variance of Poisson distribution is also equal to lambda. We know by definition mean is equal to expectation of x, and expectation of x is summation x is equal to minus infinity to infinity x into probability of fx, or probability of x equal to x, or we can write fx, that is summation x is equal to minus infinity to infinity x into f of x lambda, and it is defined only for x equal to 0 to infinity. So we can take x into, what is fx lambda? It is e ki power minus lambda, lambda ki power x divided by x factorial. So now we can take e ki power minus lambda to be common. So x is equal to 0 to infinity x into lambda ki power x by x factorial. So we can write this as e ki power minus lambda x is equal to 0 to infinity x into lambda ki power x divided by x into x minus 1 factorial. So x and x cancel out. So we can write this as summation x is equal to 1 to infinity, because at x equal to 0, the term becomes 0. So we can take x equal to 1 to. Otherwise, we can also write this as, e to the power minus lambda. For x equal to 0, it is 0. And this is x is equal to 1 to infinity e to lambda to the power x by x into lambda to the power x upon x factorial. So this is defined for x equal to 1. So we can write this as e to the power minus lambda summation x is equal to 1 to infinity. So lambda ki power x, we can write lambda into lambda ki power x minus 1 divided by x minus 1 factorial. So again we can take lambda to be common, e to the power minus lambda. This becomes summation x is equal to 1 to infinity lambda to the power x minus 1 upon x minus 1 factorial. So if we put a value of x, then what we get? Lambda e to the power minus lambda. When we put x equal to 1, it becomes 1 plus lambda upon, for x equal to 2, it becomes lambda upon 1 factorial plus lambda square upon 2 factorial plus lambda cube upon 3 factorial plus so on. So this becomes lambda into e to the power minus lambda and this is e to power lambda, and that is equal to lambda into e to power 0, and that is equal to 1. So this is lambda. So what we get? Expectation of x, that is mean, that is equal to lambda. So mean of Poisson distribution, that is equal to lambda. Now we find variance. Variance of x. We know that variance of x is equal to mu2 dash minus mu1 dash square. That is expectation of x square minus expectation of x whole square. So we have already find expectation of x, that is equal to lambda. Now what we have to do? We have to find expectation of x square. So first we find expectation of x square, that is summation x is equal to minus infinity to infinity x square into f of x lambda, that is summation x is equal to 0 to infinity, it is defined. So x square into e to power minus lambda, lambda to power x divided by x factorial. So here what we do, we try to write this x square as x is equal to 0 to infinity. We try to write x square as x into x minus 1 plus x. So it is, if we expand this, then again we get x square. But how we can write this? We try to write x square as x into x minus 1. So this is the important point to remember. We write x square as x into x minus 1 plus e to power minus x minus lambda, lambda to power x divided by x factorial. So here the important point to remember, that is x square is equal to x into x minus 1 plus x. So we can split this into two parts, x equal to 0 to infinity, x into x minus 1 e to power minus lambda, lambda to power x upon x factorial plus summation x is equal to 0 to infinity x into e to power minus lambda, lambda to power x upon x factorial. For x equal to 0 and 1, the first two terms of this expression becomes 0. When x equal to 0, this becomes 0. When x equal to 1, this becomes 0. Then the whole term becomes 0. So the summation is only defined for x equal to 2 to infinity. So we can write summation x is equal to 2 to infinity. We can take e to power minus lambda to be common. We can take e to power minus lambda to be common. X is equal to 2 to infinity. X into x minus 1 lambda to power x upon x factorial. So we can write x into x minus 1 into x minus 2 factorial. We can write this. Plus, this is nothing but this is same as expectation of x. So we can write this as e to power minus lambda, x minus 1, both are cancelled. So we can write x is equal to 2 to infinity. So lambda ki power x is written as lambda square into lambda ki power x minus 2 divided by x minus 2 factorial plus expectation of x is lambda. So we can take lambda square common, lambda square e to power minus lambda, and the expression in the bracket in the summation it become 1 plus lambda by 1 factorial plus lambda square by 2 factorial plus lambda cube by 3 factorial plus so on plus lambda, and it is lambda square e to power minus lambda, and it is again e to power lambda plus lambda. So that is equal to lambda square plus lambda. So we have expectation of x square This is equal to lambda square plus lambda. Now variance of x, that is equal to expectation of x square minus expectation of x whole square. So lambda square plus lambda minus expectation of x is lambda, it is lambda square. So again we get lambda because it is cancelled out. So again what we find, variance of Poisson distribution, that is equal to lambda. So mean and variance of Poisson distribution are same and they are equal to the parameter, that is lambda. So now the next thing is moment generating function. Moment generating function of Poisson distribution. So moment generating function. So the theorem is, prove that the moment generating function of the Poisson distribution is e to power lambda into e to power t minus 1. So e to power lambda into e to power t minus 1. So we know that by definition of moment generating function, mxt, that is equal to expectation of e to power tx. This is by definition of moment generating function. And it is equal to x is equal to minus infinity to infinity e to power tx into probability of x is equal to x. But the function is defined for only for 0 to infinity. So we can write x equal to 0 to infinity e to power t. Even we can also write this as 0 to infinity e to power tx into f of x lambda or f of x. So what is f of x lambda? It is defined for minus infinity to infinity. But fx lambda is defined for 0 to infinity, that is e to power minus lambda, lambda to power x divided by x factorial. So we can take e to power minus lambda to be common, and x is equal to 0 to infinity e to power tx and e to power minus lambda. So we can write this as sorry, e to power tx into lambda to power x. So we can write this as lambda into e to power t whole power x divided by x factorial. So when we put value of x 0, 1, 2 and so on, we get 1 e lambda to power 0 is 1, 0 factorial is 1 plus lambda e to power t divided by 1 factorial x equal to 1. For x equal to 2, it is lambda e to power t whole square upon 2 factorial plus so on. And so this is e to power minus lambda into, what is the value of this function? So this is again e to power lambda e to power t. So this is e to power, if we take lambda e to power t to be x, then it is e to power x. So we can take e to power lambda e to power t minus lambda. This is equal to, so we can take lambda to be common and then e to power t minus 1. So this is the moment generating function. So therefore, moment generating function of Poisson distribution function is e की power mxt is equal to, even we can write this is equal to e की power lambda into e की power t minus 1. So now let us discuss one example. In a Poisson distribution, three times probability of x is equal to 4, probability of x is equal to 2 is equal to probability of x is equal to 4. So find the parameter lambda. Find the parameter lambda. So for Poisson distribution is given by probability of x is equal to x, that is summation x is equal to 0 to infinity e की power minus lambda, lambda की power x upon x factorial. Now probability of x is equal to 2. It is summation x is equal to 0 to infinity e की power minus lambda, lambda की power 2 divided by 2 factorial. Probability of x is equal to 4 means it is summation x is equal to 0 to infinity e की power minus lambda, lambda की power 4 upon 4 factorial. So what is given? Given that 3 times probability of x is equal to 2 is equal to probability of x is equal to 4. So 3 times summation x is equal to 0 to infinity e की power minus lambda, lambda square upon 2 factorial is equal to summation x is equal to 0 to infinity e की power minus lambda, lambda की power 4 upon 4 factorial. So, but it is sorry, yeah, it is not in term of summation, but it is like this. Sorry, it is not. Yeah. So now 3 times of this is equal to, so we can cancel out this, lambda square is cancelled out. So 3 by 2 lambda square is equal to lambda to power 4 upon 4 into 3 into 2. So 2 and 2 cancel out. So lambda to power 2 is equal to 36. So this implies lambda is equal to plus minus 6. But lambda is always greater than 0. So since lambda is always positive, so we can take lambda is equal to 6. Okay. So therefore lambda is equal to 6. So we find the parameter lambda to be 6. So this is all about this lecture. In the next video lecture, we will talk about some examples related to Poisson distribution and how we find the recurrence relation for the moments of Poisson distribution. And then one important thing is how we can derive Poisson distribution from the binomial distribution under some condition that we have already discussed in today's lecture. So thank you. Have a nice day.